All right. At the end of class last time, we proved I think we proved the idempotent property, right? Yep. And we said that we proved the idempotent property for or, and then we proved it also for and we noted that the proofs were just parallel. And we noted that because our set of axioms are also in parallel, that anytime you prove one theorem, there is always a parallel proof using the dual axiom that proves the dual of the theorem that you're trying to prove. And so even though we did it this once to show how that works, from now on is all you have to do is just prove one of them, and you can just say by duality the dual theorem follows. All right? Now here's, I think, there's the zero theorem. One is the zero of x, because if you do x or 1, you get 1. Right? And if you do, and the zero of and is 0, because if you do x and 0, you get 0. So of course in formal methods, these are also called zero theorems, and the x 0 is false. So false is the 0 for and, right? And I think this might be an exercise for the student. I think you probably have to prove that for me tomorrow, for Thursday. And here are the absorption properties. Do you remember the absorption laws from formal methods? So now these are going to be really important. In circuit design, this has direct application to combinational circuits. Speaking of which, what is a combinational circuit?
The output depends only on the input.
Yes, it's where the output depends only on the input. So to specify a combinational circuit, what are the 3 ways to specify a combinational circuit?
Truth table.
Truth table.
Boolean.
Boolean algebraic expression.
And
What's the third one?
diagram.
Logic diagram. Okay, so what we're doing here, we did the Boolean, the truth table. With the truth table, you give the truth values for all possible combinations of the input. You give the output for all possible combinations of the input, because the output depends only on the input. Right? So there's no ambiguity involved there at all. Right? So now, here's the absorption property, x or x and y. Notice we don't need the parentheses around the x and y because it has higher precedence. Right? And that equals x. And this should be familiar to you from formal methods. And then we have x and parentheses x or y equals x. So you can prove these also. These are theorems you can also prove. Here's the consensus theorem. It is an interesting one that we're not going to use later at all, so we're not going to bother with it, but there it is. And here, I think, this will be a useful exercise to prove De Morgan's law. Because the De Morgan's law involves the complement. And so we need to have, I want to show you a technique for how to derive complements. Because what does De Morgan's law say? It says that the complement, now let's just take a look, there's 2 De Morgan's laws, right? Right. It says that the complement of A and B equals A prime or B prime. Are you with me? Now, I'm going to write down a statement here about how to prove complements. And then we're going to apply it to the proof of the first De Morgan's law. Proving to prove that some expression y, to prove that some expression y is the complement of some other expression z of some other expression z, you have to show that y and z obey the complement properties. Show that y and z obey the complement properties. Now, what are the complement properties? Do you remember what the complement properties are? The definition. We actually have, in our axioms, we have the definition of complement. And there were two of them, actually.
X or X prime equals 1?
Yes. So to show that y and z are the complements, we have to show what? To show that y and z are, to show that this is the complement of this, we would have to show that what?
Y or Z equals 1.
Y or z, so we have to show that y or z equals 1. That was one of the properties, the complement properties. But then, and what else?
And Z equals
0. And y and z equals 0. Now, is everybody clear on that? Because that was our definition of complement. Are you with me? With this system is a little bit different from our formal method system because we have a different set of axioms and different symbols, different precedents. And here we have, and one of our axioms is the definition of complement, and these are the complement properties with y and z. Now, in this first De Morgan's law, what are we claiming is the complement of what?
We're saying that A and B is the complement. Sorry, A and B complement. Sorry.
No. I think Now let's think about what it is that we have to prove. What are we claiming? What is in this first De Morgan's law? What are we claiming is the complement of what? We are claiming that. What is the complement of what?
The complement of A and B equals A complement or B complement.
Yeah, but that's not how I wanted it. You didn't say it. Because what is A prime or B prime? A prime or B prime is the complement of what?
A and B.
Close but no cigar. A prime or B prime is the complement of what?
Oh, A
and B.
Right.
Now let's think about that. Are you with me?
Yeah.
The De Morgan's law, so to prove the first De Morgan's law, we have to show that A prime or B prime is the complement of
A and B.
A and B. So De Morgan, first De Morgan,
You just read it.
first De Morgan is what we have to show. We must show that A prime or B prime must show A prime or B prime is the what?
Complement.
Is the complement of what?
A and B.
Of A and B, right? Because it says A and B, this. Are you with me? We have to show that these two things are complements. We have to show that this is the complement of this.
Easy.
Rather. Now, how do you show that this is the complement of this?
By using the property.
Yeah, so what do we have to prove? So therefore must prove what? That what?
A prime or
A
B
prime, A prime or B
in
prime.
parentheses.
Okay, in parentheses, yeah.
Or
Or
A and B
A and B
is equal to 1.
is equal to 1. We must prove this.
And we must prove
And What else? What must we prove?
That A prime or B prime
A prime or B prime
and
and
A and B
A and B
is equal to 0.
is equal to 0. And therefore they will be the complements. All right? Does everybody see this? Can we focus on the sideboard pretty good? And still see it? Okay, so let's call this one part 1, and this one we'll call part 2. Okay? So part 1. So we'll go around the class. And so we have to prove that, actually I did it in a slightly different order here. A and B, or A prime and B prime equals 1. So let's start with this, A and B. We have some unnecessary parentheses here, but that's all right. Or A prime and B prime. We'll start with the left-hand side. Equals, by commutative, boy. Yeah, okay. So I tell you what, let's do.
We can do,
By commutative, I was really picky here. I mean, this might have been an obvious step, but the first commutative, I'm just going to change the orders of these, right?
right.
So this is going to be A prime or B prime or A and B. Okay. Now, we're going to use the distributive law. And what we're going to do is this whole thing we're going to distribute this whole thing into here. Are you with me? So this is distributivity of what?
Or.
Of or
Over and.
over and. Is everybody clear on what we're going to do here? So this is going to go into here. Actually, so what's it going to be? It's going to be, let's do parentheses, parentheses. So what's it going to be? A prime.
A or A prime or B prime.
Well, this whole thing is going to be ORed with this.
Right. So A or A prime or B prime.
Yeah, I was going to do this one first. A prime, yeah, I think what you said was correct.
Or A.
Or A. Are you with me? Yeah, I know, there's some unnecessary parentheses here, but,
And.
oh, wait.
Yeah, you don't need to.
Yeah, okay. And, what?
A prime or B
A-
prime or B.
Or B, yes. Like this. Is everybody good?
And since those are all the same precedents, we can get rid of the middle parentheses.
Right, we can get rid of the parentheses, and we can use commutative and distributive.
Wait.
No, sorry, commutative and associative.
Yes.
Oh, okay.
So we can use the commutative, because what do we want to do? This parenthesis, by associative law, this parentheses doesn't matter,
Right.
and we can move this A next to this A prime, yeah?
Right. We want to do that on the B side as well.
Okay, and on the other side as well. So what we'll do is, well, let's have this be, B prime or, and then what?
A prime or A.
A prime or A, and then over here we'll do the same thing, which would make it what? We'll have an A prime or, and then what?
B prime or B.
B prime or B.
And we can use excluded middle.
Yeah, what did we call that?
Complement.
Complement. Twice, right? So what does that make? That makes this B prime what? Or what?
1.
1 and what? A prime or 1, okay? And this equals by the,
Identity of or?
No.
Identity of, never mind.
nope. We just had it on the slide a few slides ago.
The 0?
By the zero theorem, okay? Equals by the zero theorem. So what do we know by the zero theorem? B prime or 1 is what? So this is 1. A prime or 1 is what?
1.
1. And then what about this?
Identity.
Exactly. This is identity. So by the identity, this is 1. And that's what we were trying to prove, right? For the first part. Is everybody with me on this? Okay, so now let's do the second one. Part 2. So before I erase it, we'll put it down. So part 2, we need to prove this. Okay, so let's do, let's start, commutative is trivial, right? So let's start with A and B and A prime and B prime. So here we have A and B and A prime and, that's right, A prime or B prime. We'll start with this, and we want to get this to eventually be what?
0.
0. Now I'll erase this. So this equals, by the distributive law, so now we're going to distribute,
Over and over or.
yes, and over or. So it'll be this one and this, or this one and this. Are you with me? So this will be A and B and A prime, what? Or A and B
And B prime.
and B prime. And notice that we don't need parens here now, right? Because and has higher precedence than or. Is everybody clear?
Mm-hmm.
And so now, by but here, what about the A and the A prime? That's going to give us, yeah, that's going to give us 0. Yeah, so this equals by, let's do a commutative just to get them together. So by commutative, let's get this A and A prime and B, or A and B prime. So let's just get these two together. And now we know that A and A prime is 0, and we also know that B and B prime is 0. So this equals by the complement twice. So this is going to be 0 and B, or 0 and, or A and 0. Now look, you guys, do you see what, now watch this. Now do you see why they use this notation? Look how, now that you got to be careful. This is and or, it's not addition and multiplication. But isn't it convenient? Because look, if these were integers, 0 times something is what? 0. Well, 0 and anything is 0. You see why they do it? Why they use this notation? It's just kind of cool how. Yeah. How? Oh, did it the same thing here?
No, it doesn't.
Oh no, yeah, it doesn't work here because this was B or 1 is 1.
Right.
But still, this part, it's kind of slick.
This is the 0 again?
Yeah, and so this is the 0 twice, right? So this is 0 or 0, and then this is what? Identity. Identity of or, which is 0, boom. So we showed that. And what about, and now what can we say about the second?
Duality.
Here, yes, and so by duality, the second De Morgan's follows by duality. The second De Morgan follows by duality. Are we good? Now, watch this. This next one is these are the complement theorems. There's actually 3 different theorems here. What's the first one? What was the first one called in formal methods? Yeah, this is double negation, basically, right? If you take the complement of x, you get x. Now, how would you prove this? We're not going to take the time to prove it, but now look, you guys, well, maybe we should at least verbalize it. The complement of what is what? What do we have to prove? So the complement theorem.
The complement of x prime is x.
Yeah. Complement theorem. So we must prove that the complement of x prime, the complement of x prime is x. So in order to show that the complement of this is this, what do we have to show? That they follow that they obey the what?
Laws.
The complement properties, right? So what do we have? So therefore, therefore must show what?
That x and x prime.
Yeah, that x and x prime
Equals 0.
equals 0,
And x or x prime.
and x or x prime equals what?
1.
1. Are you with me? That's how you would prove it in 2 separate proofs using the theorems and axioms. And furthermore, how would you show that 1 prime equals 0?
Same thing.
You would have to show that what? That the complement of wait. What are we trying to show for 1 prime? The complement of what is what?
Of 1 is 0.
We're trying to show that the complement of 1 is 0. So what would you have to do?
Show the complement properties.
Yeah.
So that 1 and 0 equals 0.
Uh-huh.
1 or 0 equals 1.
Yeah. And then how would you, well, for the last one, you have to show that the complement of 0 is 1.
Same thing.
So you have to show the complement properties of that. You see how to do those? Okay. So you have some proofs to do using this system, and it's really important to get familiar with how to do these manipulations, because these have direct application to circuits, combinational circuits. All right. So now, what were the 3 ways to specify a circuit again? A combinational circuit? The first one was what? Truth tables. The second one is Boolean algebraic expression. The third one is logic diagrams. Now, here's how the logic diagrams work. A logic diagram is the closest resemblance to the actual physical layout of the circuitry on a chip. Because literally, what happens is, a logic gate is it's a collection of components at a lower level of abstraction to produce an actual physical gate. And furthermore, the lines that go in, the lines that connect these gate symbols on paper, they physically represent copper wires. I mean, that's how it's laid out. They're actually laid out in wires. And look here, you guys. Here are the symbols. So check it out. This figure right here that has the A and the B coming in from the left and the X going out at the right. Okay, so we have the X, so A and the B are the inputs and X is the output. And notice that what it has is it has a straight line down here, and then it has a little, a rounded right-hand side. And the output comes out of that rounded right-hand side, and the input is coming into that straight line on the left. That symbol, that shape, you can tell by the shape of it that is an AND gate, right? And then, and here's the truth table for the AND gate. that corresponds to this symbol. And then an OR gate has a curved input side. All right, a little curve here, and then it has a little pointy right side. So this shape of this gate is the shape of an OR gate, and then this is called the electrical component. This is called an inverter. Okay, in circuit design, you call this an inverter, and the thing that indicates that that it actually inverts, that it takes the negation of the input, is this little circle, right? So now, you guys, I have something for you. It's really, if you draw those things by hand, it's really kind of like hard to get them right. And so what I have here is a set of templates. And I would like for you to sign out. I'll let you use these for the semester. You should use these on your homework assignments and bring this to the exam. I'm telling you, it is so fast. Because see, look, here's the AND gate, here's the OR gate, here's the inverter. It's so fast to draw them with this. And what I recommend you do is, so here's the sign out. Take one and pass it on. So sign up for it and sign your name there. And don't lose these, they're I'll charge you $10 if you lose it. Okay, so anyway, because I had to buy them. But I probably won't. But anyway, just to keep you honest, I'll have you sign it out. But anyway, what I recommend you do is, it can be kind of, oh, you guys at the front get to pick the clean ones. So what I recommend you do is, don't bother drawing the wires with the straight edge. You can be really fast if you need an AND gate, and then you can just draw the wires freehand. You see what I mean? And you might think that this would slow you down, but this will speed it up. This will speed it up, and it'll make life a whole lot easier. So I recommend that you do all of your homework assignment for Thursday requires to draw some logic diagrams. I recommend you just, use these. Okay, does everybody see that what each one of these, the shape of each one of these, and what the truth table is, right? Now, here's the thing, you guys. Everything can be constructed with just an AND gate, an OR gate, and an inverter. But in practice, these are not really considered very fundamental. In practice, we have another set of gates, 3 gates, that are very common. In fact, really more common. In fact, watch this. Now, what did we say that little circle meant in the logic diagram? Inverter, negation, right? Now look, what is this first gate on the left? This pointer is useless. Yeah, first of all, it looks like an AND gate, but what does it have extra?
The inverter? That
little inverter on the output. So what does that mean? That means it first does the AND, and then what does it do? It inverts it. So that's called a NAND gate. Are you with me?
So the triangle doesn't really do anything.
Well, except that the triangle, you use the triangle here for the inverter.
It just represents
Yeah, it's actually what they call a buffer. There actually is a use for an inverter there actually is a use for the buffer without the inversion.
Okay.
It has to do with fan out.
Okay.
Don't need to be concerned with that right now.
Okay.
But it's the little circle is the one that does the inversion. So does everybody see then that this represents and then inverted? So now, if A and B are 0, 0, 0, 1, 1, 0, 1, 1, if the values of A and B are 0, 0, 0, 1, 1, 0, 1, 1, what would the AND be? What would AND be in order?
0, 0,
0, 0, 0, 1. So inverted, that's what?
1,
1, 1, 1, 0. Do you see how that worked? Mm-hmm. And now what gate is this? NOR. So now on the template, you would draw the OR, and then there's another little circle, inverter circle. And then stick a little inverter circle on it. Are you with me? So that's an OR gate. So OR, what would it be? What would be A or B be? It would be what? 0, Hello? It would be what? Well, if A and B have the values 0, 0, 0, 1, 1, 0, 1, 1, then A or B would be what? 0, 1, 1, 1. So inverted, it would be what? It's 1, 0, 0, 0. Are you with me on that? And now the last one is an exclusive OR gate. And we abbreviate this, the letters for this are XOR. XOR stands for exclusive OR. And there is not an exclusive OR symbol there, but there is an OR symbol. So how do you draw this on your paper? You draw the OR, and then you just do what? Shift your template a little bit to the left, and then duplicate that curved line. Are you with me? So that's an XOR gate, exclusive OR gate. And the mathematical symbol for that is a circle with a plus in it. Because plus, in this system, is OR, and so you put the circle around it, that makes it exclusive OR. Are you with me? Now, what is inclusive OR? When is OR true? When A is true, or what?
B is true.
Or what? When A is true, or when B is true, or what? Or when they're both true. But when is exclusive OR true?
Only when one.
When one is true, or the other is true, but what? But not both. So it's one is true exclusive of the other one. Are you with me on that? So does everybody see that this is the truth table for exclusive OR? Actually, in formal methods, what is this function? What is the exclusive OR function? How do we do that in formal methods? This here, this symbol, this operator in digital circuit design is the same as what in formal methods? Well, what do A and B have to be in order for this to be true? They have to be what?
Opposite.
They have to be different. So they can't be what?
They can't be the same.
They're not the, so, yeah, so what is it? Yeah, it's not, yeah. The way we did this in formal methods was this. Not equivalent. Right? Are you with me? Does everybody see how that works? Okay. Now, furthermore, if you're stranded on a desert island and the only thing you have is an AND gate and an inverter, and you want a NAND gate, you can always do what?
Get rid of the button.
You can always hook up your inverter as the output of the AND gate, and that's equivalent to a NAND. Do you see how that works? But let me tell you a story. Guess what? Guess what happens in real life? In real life, this is not how you make a NAND gate. Because in real life, in the real world of circuit design, it takes fewer transistors to make a NAND gate than it does to make an AND gate. And so guess what happens in real life?
Well, it's more of those.
Well, in real life,
Oh, you'd use that.
you make a NAND gate, and then you have to do a what? Put an inverter to turn it into an AND gate. So it actually takes more real estate, circuitry real estate, to make an AND than it does to make a NAND. Are you with me on that? You see, that has tremendous practical implications for digital logic design. Is everybody, are you with me on that? You see? Yeah, because you have to throw in an extra transistor. I mean, you can make a NAND with fewer transistors than with an AND. It's just a fact, that's an engineering fact of life. Now that we have this exclusive OR, we have to specify its precedence. And so the precedence of exclusive OR is between AND and OR. All right? So when you see an expression with an XOR in it, it's in between AND and OR. Is everybody clear on how that works? Now, what we've shown so far are two input gates. But these gates, all of these gates come with more than two inputs. It's frequently useful to have more than two inputs. So this is an example of a 3-input AND. Are you with me? What's the truth table for a 3-input AND? It's only true if what?
All three.
All three of them are true otherwise. Are you with me? And then here is, okay, and the same way with OR, by the way. What would the three input OR be?
All of them except for none of them.
Yeah. Okay. So, yeah. Right. All right. And there's a 3 input NAND, a 3 input NOR.
What's the 3 input exclusive OR? Is it
Well, yeah, and exclusive ORs, you normally don't think of that as it's possible, but you rarely see a 3 input XOR on a circuit diagram.
Right.
It's not as,
But out of curiosity, the truth table would be only when A is true, only when B is true, and only when C is true, right? So
actually,
C is only true.
well, okay. Check this out. A XOR B, it equals A and B prime or A prime and B. And it's true when one of them is true, but not the other one. And furthermore, see, look, if you want to generalize it, here, if this is an AND gate, and this is an AND gate, then if you put two input AND gates together like this, if this is A and B and C, then what you get out here is A and B and C.
Okay.
So that's how you can make a 3 input AND out of a two input ANDs.
Okay.
And so the question is, what if you had an exclusive OR,
That'd be the same thing.
how would you, yeah.
Okay.
And so you can explore that. Actually, that would be a nice little thing for you to explore. Good question. And that does have practical application in cryptography, actually. So anyway, now there is also a set theory representation of this logic. And what happens is, do you remember how we had a meta theorem in formal methods?
Yep.
For sets? Do you remember we had a bunch of theorems that dealt with union and with intersection? Union and intersection. And do you remember we had a meta theorem that said, well, if you have a set theorem, a theorem that has to do with sets that has unions and intersections and da-da-da, it was a theorem if and only if what? There was a recipe.
You could like translate it to a Boolean.
To a Boolean expression, and then there was a recipe if you only had unions and intersections and complements, then there's a recipe to translate it to
Ors and ands.
to ands and ors, and that would be a theorem if and only if this was a theorem, or if that was a theorem, then this was a theorem. Well, so there is this set theory representation is basically that, all right. So the correspondence is an OR gate corresponds to set union, an AND gate corresponds to set intersection, and an inverter corresponds to set complement. And here's something that's really cool. This is a set theory representation of the absorption law. Because what did we say an absorption law? What absorption law does this slide represent? Well, do you see that if we have X and Y and we draw a Venn diagram and X is shaded like this? Are you with me? And then do you see that X and Y is shaded like this? Now what happens if you take the union, what happens if you take the union of this set and this set? What do you get?
X.
You get this set, considering it to be unions, right? But we said that the union corresponds to OR, right? So what we're saying here, but this circle is the same as this circle. So basically what this is illustrating is what? It's illustrating that X or X and Y equals what?
X.
Equals X. So that's one way to visualize that this is how you can visualize this absorption property with Venn diagrams. Kind of another way to look at things. Okay? And now comes a really important concept. Those three ways, now look you guys, those three ways to visualize, those three ways to specify a combinational circuit, two of them are alike and one of them is different. They do not have the same property. And this figure is really an important one to understand. What this figure says is that there is a one-to-one correspondence between a Boolean expression and a logic diagram. Now, what does that mean, there's a one-to-one correspondence?
I mean, they could be written in either way exactly.
Exactly, yes. For every Boolean expression, there is exactly one what? Logic diagram. And for every logic diagram, there's exactly one what? Boolean expression. But I'm here to tell you that for a given truth table, there's not just one logic diagram or Boolean expression. Instead, the truth table is more general. Do you see what I mean? The truth table is general. A logic diagram and a Boolean algebraic expression are specific. And there's a one-to-one correspondence between each one of those, but not between a truth table. Are you with me on that? Does everybody see that? That's a really important concept, yeah.
Are there an infinite number of Boolean expressions for everything?
Yeah, because you could always OR it with 0. Whatever expression, you could OR with 0 an infinite number of times. So there are an infinite number of. And this is the heart of digital design, because look, what does in digital circuit design, what do you always want to do? Anytime you build anything, how do you want to build it? Do you just have infinite resources? Anytime you want to construct something, anytime you want to engineer something, how do you want to engineer it? Yeah, the least material possible, right. So you see, in other words, optimizing the design is a central problem on how to construct logic diagrams for computers. And so we have all these infinite number of Boolean expressions, logic diagram pairs. Right? So now what we need to do is we need to see how to make the connections between these three different ways to represent a combinational circuit. Now, here and so now, what did we say gets paired? A logic, which ones go together?
Boolean expressions and logic diagram.
Yeah, Boolean expression and logic diagram. So here's what we need to be able to do. We need to be able to, for every Boolean expression, we have to be able to do what?
Create a logic diagram.
Draw a logic diagram. And furthermore, for every logic diagram, we need to be able to do what? Write down the Boolean expression. It's really easy. It's really easy. The AND gate corresponds to the AND operation. The OR gate corresponds to the OR operation. The inverter corresponds to the complement operation. And it's really easy. Now look at here. Suppose I give you, actually I should maybe do, here. I should not show you this. Let me write down a Boolean expression. A or B prime and C. Let's just consider this Boolean expression. Well, here's a B and here's a prime. So what are we going to, assuming that A, B, and C are coming from the left, what are we going to have to do?
B needs to be negated.
B is going to come into an inverter, right? And then the output of that inverter, and which one of these happens first?
That one.
This one. So then what's going to happen?
Then it needs to
The
be ANDed.
output of the inverter has to be ANDed with C, and so what kind of a gate? Obviously, an AND gate. And then the output of that, and then what happens?
That output
A has to come in
into an OR gate with the output
Yeah. Now, did you see how to do that? Do you see how you would do that? Here it is. Are you with me here, how this worked? So here, B comes in, it goes to the inverter. So if B is the in, we can write, look, we can write a Boolean algebraic expression at each one of these junctions here. Are you with me? So if this is B coming in here, then B prime is what's coming out here. Then we have C coming in here and B prime coming in here. We add those, we have B prime. Oh, by the way, notice that sometimes we omit the dot, just like in algebra. We omit the multiplication dot. Are you with me there? Okay. And then if we, to OR this with A, we bring A in here and we OR that with that, and so that's A or B prime and C. Are we good? Now, how would you do this one? Let's think, how would you do this one? Let's do AB. So let's do AB. I have some unnecessary parentheses. No. Let's do AB or BC prime, BC prime. Sometimes we put the dot in. Let's do A and then the whole thing primed. Now, can you draw this with your template there on your notes? Try to draw this. So you typically have A, B, and the inputs coming in from the left and the output. That's the convention. The convention is to have the inputs from the left, outputs to the right. Sometimes the inputs come from the top and the outputs go down. But usually that's there. So what would it be like?
Well, first you have to complement the C.
Yeah. Then you have to do what?
And it with the B.
And it with B. And then you have to do what?
And the A and the B.
And the A and B. And then you have to do what?
Or it.
Or that. Now here's a tricky thing. But then you have to do what? You have to AND that with A. But wait a minute. There's an A here and there's an A here also.
Well, also earlier there's two B's.
Oh yeah, and earlier there's two
You have
B's.
to split them.
Yeah, now that was, yes. So what happens is, here's how the signals work. Here's how the signal works electrically. The way it works is like this. What happens is, you can tap off. Now, do you guys know the difference between current and voltage? Now, you know, you took physics 2. Did you take physics 2?
Yes.
Do you know the difference between current and voltage? Which one corresponds to pressure and which one corresponds to current? Well, I meant flow of, well, anyway. Which one corresponds to pressure? It's the voltage. The signals here are voltage signals. They're not current signals. So what this means is that when you have A coming in here on the left, you can tap off of it, and then that A can be available here. Do you see how that works? And so here's A and B, so here's A and B. So B is coming here, you can tap off of B. And we're going to do this in the lab Friday. You're actually going to stick the wire in the same place as this one and tap it out. Do you see? Because these are wires, right? And then here's C prime, then C, B and C prime, then here is A or, and then here's A and B, or B and C prime. And then here is A, so that's with A, and then here's the inverter for the whole thing. All right? I asked you to get started. And anyway, here's the whole thing. And now I think you have enough. Oh, just let me do one more thing. Do you see that anytime you have a variable, you can always just throw in an inverter to get its complement, right? And furthermore, anytime you have an A coming in here, you can always tap off of it. So typically what we do is we abbreviate the logic diagram. And so that big complicated logic diagram, this is an abbreviation of the exact same diagram. Instead of having the A and the B and the C and then tapping off and making it all complicated, we just put the A here, and then here we just put A here. Do you see how that?
You just list B twice.
And and here's B, and we know that we can always just have one B coming in and tap off of it. And furthermore, if we have this inverter here, we could just make this a NAND. You know what I mean? So any signal can be duplicated by a junction of two wires. The complement can be produced by an inverter. So this is an abbreviation of the same. And we frequently, this is a common practice in circuit drawings.
What about the C though? Because it was immediately negated.
Well, you can just put prime here. You just put C prime there. Because you know that what that means is that C coming in, you just throw in an inverter and make it a C prime.
You
So
don't have to actually draw the inverter.
yeah, that's what I'm saying. You can abbreviate it by not having, but if you are doing this in a lab, you would have to put the inverter there,
Yeah.
you know. But that's an abbreviation of the diagram. All right? Good deal. That's it. See you Thursday.